All right. So a couple of activities today. Again, you guys have pretty much seen everything you're going to see, all the new material. I would highly recommend. I've said this a lot lately, but really, if you haven't started that final project, you should. It's long. It's not. I think at this point you won't find it super hard, but it's very long. So, you know, if you put this off, like, you know, you're studying for the exam, but you might take a look at the reactions on there that are from 7, 8, 9, and 10, and they will working those problems on the final project would help you study. And then, you know, I'm not trying to scare you too much. Like, you have plenty of time if you start, but just don't. If you take exam 3 and then go home and don't think about organic chemistry for 10 days, it's going to be kind of hard. We will meet via Zoom Tuesday and Thursday, but it's going to be a review, and I'll throw some problems up, and you can work them. There's not going to be any new material after. It's arguable whether today is new material or not. Okay, so a question I've gotten a lot, so I don't think I did it very well. I have in my notes that I did it. That's never a great. You see the quality of my notes here. I'm always embarrassed when students are like, can I, you know, the student misses a class and like, can I get your notes? No, my notes are terrible. You always want to make friends in class. So this whole reaction where we've been, you know, go back to the very first one. If we add HBr across the double bond, the reverse of an E1 elimination, that reaction, if you go through this mechanism, starts with the alkene acting as a nucleophile or a Lewis base. And so anything that makes that alkene more electron rich will make it more nucleophilic. Anything that pulls electrons out of the alkene will make it less nucleophilic. So when you look at substituents, you want to consider what the effect of the atom is. So let's look at two here. There's that one. So go ahead and draw the products of these. Product, parenthesis, S. And then judge which one you think would go, which of the 3 reactions you think would be fastest, which of the 3 reactions you think would be slowest. How many products do you think you're going to... So up here on the top one, it doesn't matter where you put the H and the Br, right? Because they're both secondary. You're going to get a secondary cation either way. You're actually going to get the same cation. If I protonate this carbon, or if I protonate that carbon, I get a cyclohexane cation, bromide adds to it. There's only one possible product. On the next two, there are 2 possible products. could get either one of those. You only get one. So take another look. If you drew more than one, if you drew them both, take a look at your mechanism. You don't have to draw the whole mechanism out, but think about the mechanism, see which one of those you think you'd get. You'll just have to. So close. Same thing is true on the bottom. You're only going to get one of those two products. All right, so on the middle one, the one with the oxygen in the ring, which one do you get, left or right?
Right.
Got one right. Rights. The right side of the room, from where I stand, is saying right. You guys, the left side, saying left. All right, so draw the cation. Think back from the cation. For this one, the cation had to be here, right? The bromide winds up attacking the positively charged carbon. So this cation leads to that bromide here, that cation. That make sense? So as you think backwards through the mechanism, the bromide's going to be attacking the more stable, or be attacking the positively charged carbon. So which one of these cations is better?
Left.
The left is better. So the left product is all you see here. The reason for that is you can delocalize that positive charge. So this cation actually has a resonance structure. Looks like that. That cation actually looks like the resonance structure with positive O. Right? The carbon-oxygen bond length is that of a carbon-oxygen double bond, close to it. The carbon and the oxygen are trigonal planar. Obviously the carbon is going to be, right? But the oxygen is too. The lone pair sticks right out in front. Sorry, not sticks right down. All right. So that, you're going to get one product there. How about on the bottom? So do the same thing. Draw the cations that you would get leading up to those bromides and ask yourself what you think about them. Okay, so again, the one on the left, the carbon that has the bromide would be positive. Molecule on the right, just get that plain secondary cation. This might be a little trickier. So what do you think about this one? Which cation is more stable? Yeah, not.
The right one?
How come?
Because the left one has a resonance structure where there's a positive charge on that.
Positive on the O, right? So there's a resonance structure here, and this is tricky. The reason I say it's tricky, right? So if we look at this, we can take the pi electrons, make a double bond there, you need to consider the entire octet. So that O is positive. And just up above here, I said, well, the O being positive helps it, right? I guess I should draw the full Lewis structure too here. So these two positive O's are not the same. In the middle one here, it's a formally positive oxygen, but the oxygen has a full octet. So it's got as many electrons as it can have. Really, the molecule has a positive charge, but the charge is delocalized by virtue of one of these lone pairs actually interacting with the vacant p orbital on the carbon. On the bottom structure, this resonance structure that has a positive O, so you might think, well, down there the charge is delocalized as well. And it is, but that oxygen doesn't have a full octet. So you guys need to, like I said, this is a fairly subtle difference. You can't just say a positive O is good or bad. A positive O, where the O is using its electrons to stabilize a positive charge, is good. Here, this O is not using its lone pairs to stabilize the positive charge. The pi electrons that are shared with it are. And so on the bottom example, the oxygen doesn't have a full octet. Oxygens that don't have full octets are very, very bad. Okay, they're very unstable. And so another way of thinking about this, I don't need to draw it. Another way of thinking about this cation is you've got a positively charged carbon bonded to a carbon that's got a really strong partial positive charge. Right? Remember, there's another resonance structure where we take the pi electrons and push them up onto the oxygen, and that would give us this. So now the O is negative, it's got a full octet, but we wind up with two formally charged positive atoms bonded to each other. That is also really unstable. All right, so that on the bottom, this bromide, on the bottom we would end up seeing only the right structure. Make sense? Again, addition of HX is always going to follow Markovnikov's rule, which, again, Markovnikov, living in the 19th century, put it down to H goes on the less substituted carbon, X on the most substituted carbon. Really, the essence of Markovnikov's rule is these reactions always go through the most stable carbocation. Okay, so you can backtrack. If we get a bromide by addition of HBr, that Br had to have gone onto a positive atom. So think about that cation and judge its stability. Okay, so what do we think about rates? Sorry, is that... Yeah.
So if there was like a methyl group coming off of where the Br is on the left one,
Mm-hmm.
would it like immediately be the left structure that you see as the
On
problem?
the bottom?
Yeah.
I will answer that,
Okay.
but I'm going to talk about other stuff first. Remind me, throw something at me if you need
Okay.
to. All right, so which of these is the fastest reaction?
Middle one.
Got definitive confident statements for the middle. Anyone want to chime in for like rank choice voting here? Okay. So middle one we're saying is the fastest. Which one is the slowest?
Bottom.
All right. So really we're comparing having an O in the ring, or an O bonded to the double bond with a carbon that's got a couple of hydrogens, and then a carbon that's got a double bond O. And so you guys are right. The middle one is the fastest reaction. The bottom one is the slowest reaction. The one with the CH2 there is the medium one. And in fact, so Audrey, this is the answer to your question. I don't really know. And the reason is, this one down at the bottom is so slow that it doesn't really happen. All right, so I'm not going to ask you, there won't be a straightforward, thinking about the exam, if you've looked at the old exams, if you look at our exam too, there's going to be a page of just a bunch of reactions you got to fill in a product for, right? I'm not going to put an alkene HX on there that won't do this. right? There might be, you know, the more complex questions where you have to explain some observations, there might be one in there. But really, this carbonyl slows this reaction down to the point that you can't really add HBr across this double bond barely. And so even if you had a methyl group here, you wouldn't likely see it. But I get, so more your point is, and I guess the trickier one might be if you put a methyl here, right? You would still end up getting the Br here. All right, so the effect of this oxygen on the double bond is a lot stronger than having a methyl.
Okay, so it wouldn't always follow, like Mark.
It doesn't follow, there are definitely exceptions to H on the most substituted, H on the less substituted, X on the most substituted. There are no exceptions to it goes on the best cation.
Okay.
Right, so that's what I mean. Markovnikov's rule as it stated in Klein, as Markovnikov published it, was a huge advance, but he was still missing something. You've got to think about it in terms of the cation. Okay, so reactions that go through carbocations go through the more stable carbocation. And so the other way to think about this again is how nucleophilic or basic is the lone pair, the pi bonding pair here. And to see that, what you want to look at is, do the groups on the double bond push electron density into the pi system, or do they pull electron density out? Right? There's 2 pi electrons in all these. There's 2 pi electrons in that alkene, and that alkene, and that alkene. But where are they is the question. And how much electron density is in there? So I'm going to erase some stuff, maybe. Erase this cation, erase the one we don't get. Actually, I'm going to erase this one too. Okay, so if we think about this oxygen, it's got lone pairs. The lone pairs can line up with the pi bonds, right? If you think about resonance, so here's a pi bond, right? Shaded, unshaded. There's a pi bond. To have resonance, for anything to have a resonance structure with that, there's got to be something over here. There could be I'm going to put this in a different color, right? There has to be an orbital here. Could have electrons, might not have electrons, right? If that orbital is vacant, you have an allocation. Right, so if I have a cation there, I've got resonance. But really what that resonance arrow is saying is I've got 3 p orbitals all interacting. If there's a lone pair here, that's a negative charge here. And again, I've got this orbital can interact with that. Or a radical. There could be 1 electron there, and I'd have an allo radical. You get the idea. Okay, so what you need to have resonance is a lone pair next to a pi bonds next to pi bonds, vacant orbitals next to pi bonds. They have to be bonded to each other. So the lone pairs on this oxygen are actually in resonance with that double bond. Okay, so if we show the arrows here, the lone pair pushes electrons in there, and we end up with a resonance structure that looks like that. Right? That's a real resonance structure for that starting alkene. And when you look at that, you've got more electron density in the 2 alkenes. This carbon is going to be the one that grabs an H. Right? Negatively charged carbon is going to be a stronger base than a neutral carbon. So the 2 electrons, and especially the atom that actually ends up being the nucleophilic atom, has more negative character to it with that oxygen there than it would without it. Right? So we're going to call this oxygen is going to be called an electron donating group. I didn't actually put that up over here. So an electron donating group. It's donating electrons into any pi system it's bonded to, which makes that pi system more nucleophilic. You're right. I'll let you write. So if you have an electron donating group on a pi bond, that pi bond is going to be more nucleophilic than it would be if you replace the electron donating group with H. All these comparisons are always going to come back to H. I said this way back at the beginning of the semester that, you know, what is a substituent? A substituent is something that's bonded to a molecule that's not an H. You sort of take your carbon skeleton, you assume it's just got hydrogens on it. If you pull a hydrogen off, put something else on it, that's a substituent. Okay, so on the bottom then, and this is why this is the faster reaction, right? That oxygen's making this pi bond more nucleophilic. That's the rate limiting step, is grabbing the H off HBr. And the other way to think about it, you can either judge it from how nucleophilic is the alkene, or you can look at the intermediate cations, right? The more stable that intermediate cation is, the faster the reaction's going to go. So the same thing here. If you're going to draw a resonance structure on the one with the carbonyl, you're not going to pull electrons away from the carbonyl. Right? The good resonance, the better resonance structure there would pull those pi electrons out. Let me actually stop. I don't want to draw that one. So let's just take the pi electrons. This is the simple carbonyl resonance structure. Every carbonyl has this resonance structure. Right? You just pop the pi electrons up on the oxygen. Carbon-oxygen bond is polar. The single bond is polar. The double bond is polar. So if you pull the pi electrons in the carbonyl up onto oxygen, you get this resonance structure. This will be important in organic too, where you have nucleophiles attacking the carbonyl. Right? That carbon, the carbonyl carbon has significant partial positive charge. So if you have really strong nucleophiles, that they can add into the carbonyl. Not yet. So having a positive charge bonded directly to that alkene makes it a little clearer how not basic that alkene is. And you can draw a resonance structure that explains that. You can move the pi electrons there. So there's your resonance structure. Now the two electrons in that alkene, one of them bears a positive charge in the resonance structure. In both cases, the electrons are being pulled away from the pi bond. So we would call this an electron withdrawing group. The carbonyl itself is an electron withdrawing group. Okay, so an electron withdrawing group. Going to make the pi bond or the pi system it's bonded to less basic or nucleophilic. On the flip side, right, so you can't just memorize, you guys can't because you're in Orgo 1 and you have exam 3 coming up, which is electrophilic additions to alkenes. So pretty much all the reactions we've talked about so far, an electron donating group will accelerate because the alkenes being the base. Right, but you can't just say all reactions go faster. There are reactions where the alkene is actually the electrophile. Okay, so if you imagine adding a nucleophile to the alkene, this one on the bottom is the only one on the board that will do that. Okay, so turn it around. Okay, so how do they look? What do they look like? A strong electron donor strong electron donor is going to be like what I just showed over here. The atom that is directly bonded to the pi system will have a lone pair. Not that the thing bonded to the pi bond somewhere out there has a lone pair, right? On the bottom here, this group bonded to the pi bond, there's an atom with a lone pair. But the atom with the lone pair is not directly bonded to the pi bond. It's farther away. And then weak electron donors you already kind of know, right? So a tertiary cation is more stable than a secondary cation. And the reason for that is the methyl groups, or the alkyl groups bonded to that carbocation are electron donating. Weakly, right? They donate electrons by hyperconjugation. That's not as good as I've just got an extra couple of electrons in my pocket I can give you. Minute 41. Yeah.